we're gonna begin with a thought experiment. Here it is. It says this. I have 4 humans pulling in picture 1. Let's assume all these humans are clones. They're identical. They all pull with the same force, just to make the math nice. And then I have situation number 2. The tension in the rope in the bottom case is A, greater than, B, the same as, or C, less than the tension in the top case. You know what? We get to vote. Once again, how high you hold your hand up, Rowan, is how sure you are of the answer. I'm positive! I'm pretty sure, but I don't know why. I'm only voting because Mr. Duke will make fun of me if I don't vote, and Mr. Duke will make fun of you if you don't vote. Got to have a hypothesis. So, the tension in the rope in the bottom case is, who says A, twice as many people, twice as big, greater than, A, greater than, A, Mr. Duke, it's got to be A, greater than, A. 8 people, got to be A. No one. Who says B? Why? B is correct. Why? Why? There's a word I'm looking for that starts with the letter A. As soon as you say balanced, this... Okay, if A is 0, the forces are balanced. And if I have, let's say if each person pulls with 1,000 newtons, if in the original diagram I have 4,000 newtons that way, then I still have 4,000 newtons that way, and I have 4,000 newtons that way. Now you might think that's 8,000 newtons, but how hard must this pole be pulling that way if the forces are balanced? And so if this is... Are you seeing what I'm really doing? I'm saying if you look at the free body diagram parts of it, it's an identical situation. But also, do you realize 2 weeks ago, all of you would have picked A. You've come a long way. I'm proud of you. Well done. What law is that? Now, if you say A equals 0, so forces are balanced, I would give you full marks. If you just said forces are balanced, I might give you like 1.5 out of 2 if it's a 2-mark question. The key is, how do you know they're balanced? Because no acceleration. What law is that? Sorry? You're right. So, you know what? I tend to abbreviate, so I'm going to go Newton's first. Okay. Today is types of forces. We're going to look at 2 main types today. I already talked about one a little bit last lesson, the gravitational force. Gravity. What was the symbol that we used? We used a capital F with a lowercase g. Force of gravity. How did we calculate the force of gravity? What was the equation? I did give it to you on your formula sheet, but it really came out of F equals what? But what letter did I use instead of A for gravity? To show that we were using the G value of 9.8. Okay. Direction. What direction does gravity act? Now, I won't mark you wrong if you say down, but please understand when you point like this, people in Australia would have an issue. So I'm going to be a bit fussier, and I'm going to say toward the center of the planet, and that takes care of down. That also takes care of people that for them that would be pointing what we would consider left and right with our frame of reference, but once we got there we would consider it down. But if you said down, Kenley, I'll give you full marks, but I can't not be a bit pedantic here and say let's be careful. What was the other word for the force of gravity? No, that's the formula for the force of gravity. What was the other? Sorry?
Wait.
No, now. Wait, no, now. Come on. Okay. Another word for the force of gravity, and this is important. I am going to ask you this on the test. On a test on forces, I will absolutely expect you to distinguish between weight and mass. Mass is measured in what units? I still wanted to ask Antonio a question as he took a bite, but I won't. Mass is measured. What are the units for mass? Kilograms. What are the units for weight? It's a force. Newtons. And please don't tell me they're the same thing. So, Shelby the ballet dancer has a mass of 45 kilograms. What is Shelby's weight in newtons at the Earth's surface? We would say weight, which is Fg, is mg. Her mass is 45. It's going to be 45 times 9.8. I think I can do this in my head. It's going to be 450, take away 9. Double check, is it 441? Yep. Units? Newtons. Now, the imperial unit for weight, for the force of gravity, in fact, the imperial unit for force is pounds. So given that 1 kilogram of mass corresponds to 2.2 pounds, what's Shelby's weight in pounds on the Earth? So we're going from kilograms to pounds, and I realize we're going from mass to force because, unfortunately, scales are inconsistent. Kilograms is a unit of mass, pounds is a unit of force, but they've just collaborated this. They've marked the scale accurately, so it works. So if I go write down what they gave me, 45 kilograms. I want kilograms to cancel. Where am I going to put it? By the way, I'm reviewing unit analysis from way back when in September. Where am I going to put kilograms? On the bottom. And I can put pounds on the top. And I guess 2.2 pounds is 1 kilogram. Am I going to multiply by 2.2 or divide by 2.2? Am I going to multiply by 2.2 or divide by 2.2? And how do you know? Why multiply? On the top. If it ended up on the bottom, then I would know I had to divide by that number. That's still to this day how I do most of my conversions. I write it out. Oh, I divide. I multiply. I can do this in my head. 45 times 2 is 90. 45 times 0.2 is 9. Is this 99 pounds? A little thin, but it's a ballet dancer. Okay. C. Here's a tough question. What would Shelby's mass be on the surface of Jupiter? You all know the answer and you don't need a calculator. What would her mass be on the surface of Jupiter? 45. What's going to change? Not her mass. Her weight will change. And for that, I would need to know what little g on Jupiter is. Oh, I bet you that's part D. What would Shelby's weight be on Jupiter? Now, Jupiter doesn't have an actual surface. It's a gas planet. But if you calculate its radius and you stood right where it starts, we'll pretend that's the surface. If there was something that you could stand on right there, maybe there was an ice thingy or something you could stand on. Humor me. It's a gas giant, and I realized you would just keep sinking. But if you were standing on a planet the size of Jupiter with the same mass of Jupiter that was made out of solid rock, what would her weight be? It's going to be 45 times 25. 1,250? Double check me. I might be off. Am I off? 1,000. Ah, no, not 250. I forgot to divide it by 2. 125. 1,125 newtons. So, what's the same anywhere in the universe? Mass. What's location dependent? Weight. No, not weight. Okay. There's some questions in the homework that ask you they're just conceptual questions, and they're asking you to think about that. You can tackle that in a bit. So force number 1, we talked about it last day, gravity. But now we can talk about another force. This one is a bit confusing, but it's very important. It's called the normal force. It's called the normal force not because it's normally there, although it usually is. The word normal is a math word. When two lines are normal to each other, they're at right angles to each other. Suppose a truck is sitting at rest on the ground. Draw a free body diagram of the forces acting on it. Okay, I'll draw the truck right there. What are the forces acting on it? Get the obvious one. How big is mg exactly? First of all, what are the units for mg, for the force? Did I give you the mass of the truck? Everybody say no. Because what units did I put there? I gave you the weight. I can tell you right now, 12,000 newtons. Is this truck sinking to the ground like quicksand? Is this truck flying to like Superman? So there has to be a force pointing up the same size. And today we're going to give that force a special name. All of you right now, with your non-writing hand, push down on your desk. Feel the desk pushing back up on you? Push harder. Feel the desk pushing back harder on you? Push even harder. Okay? That force that a surface pushing back exerts, we call that the normal force. So I'm going to draw an arrow pointing up, and I'm going to write this as F with a subscripted N, the normal force. And this is 12,000 newtons. What's the normal force? It's the thing that keeps you from sinking into a surface. It's the force that the surface must push back against an object pushing down on it. Suppose we add a 2,500 Newton piano to the back of the truck. Draw a free body diagram of the new forces. Okay, here's the truck. We already had 12,000 newtons down. What did we put in the back of the truck? A piano. What was its weight? Is that a weight or is that a mass? How do I know? I gave it to you in newtons. So there's another downward force. I'll put it right beside there of 2,500. By the way, I'm putting it beside there because if I drew it right on top, it would be a little weird. You'd miss a line, right? What's the total downwards force acting on the ground? Do the math in your head. Loud and proud, what? 14,500. Is the truck and piano sinking into the ground like quicksand? Is it flying to you like Superman? So there has to be a force pointing up. And you'll notice I drew it bigger than the 12,000. In fact, if I was really fussy, I should try and draw it the same length as the 12,000 and the 2,500 put together. And I kind of tried to eyeball that because it's canceling Kenzie out both of those. This is the normal force. This time, it's 14,500 newtons. I know it has to be there because of Newton's first. Otherwise, the truck would be sinking into the ground like quicksand or flying at you like Superman. What's the normal force? It's the force that a surface exerts against an object when that object pushes against it. Logan, can you stand up, please? Logan, behind you, can you walk to the space of wall behind you there and seriously push hard against it, please? Push. Are you sinking into the wall like quicksand? Keep pushing. Are you sinking into the wall like quicksand? Are you flying off of the wall like Superman? But can you feel the wall pushing back on your hands? The wall is exerting a normal force. How hard? I'd need to know how hard Logan was pushing. If Logan was pushing with 100 newtons, the wall was pushing back with 100 newtons. If he was pushing with 101.63 newtons, the wall was pushing back with 101.63 newtons. How do I know? Because he wasn't sinking into the wall or flying off of the wall. This is a weird one, Jagger. People saying, how can an inanimate object exert a force? It does. It must. Has to. Otherwise, Newton's first is wrong. So, this force that the ground or any surface, a table, the chair that you're sitting on, etc., pushing up to prevent the object from sinking into it has a special name. We call it the normal force. Symbol Fn. Yeah, we've turned the page now, Jackson. For what it's worth, this is a reactive force. If remember the whole, for every action there was an equal opposite reaction that I hate, but we would classify this as a reaction or reactive force. It's the result of Newton's third law, which was forces come in. So I had Logan push against the wall. Logan pushes against the wall. What does the wall do? Pushes back against Logan. And that's the normal force. Because it's a reactive force, it's not initiating anything. It's just responding. It's only as big as it needs to be. What if Logan had pushed with 151 newtons? How big would the normal force be? What if Logan had bulked up and pushed with 319 newtons? How big would the normal force be? 319 newtons. It's going to be as big as it needs to be. And here's what it means. The normal force, which is going to be a very important force for the next few weeks, I don't have an equation for it. There is no equation. Instead, we're going to do a big free body diagram, a good free body diagram, and we'll figure out how big the normal force has to be by looking at all the other forces. Okay? It's the force that prevents us from falling into the ground. How big is the normal force in the following situations? So here we have a box sitting on the ground. What are the forces acting on this box? Get the obvious one. Get the obvious one. What? Gravity? Is this box sinking into the ground like quicksand? Is it flying into you like Superman? So the forces must be balanced. There's a vertical force up. And now we're going to call that the normal force. And I can tell you exactly how big the normal force is. Can you see it? How big is it mathematically? No, 10 kilograms is not a force. How big is it mathematically? Exactly as big as mg. So here, let's write, how big is the normal force? It's going to be mg, and you don't need a calculator for this because it's 10 times 9.8. I'm hoping all of you can do your 10 times table in your head. How big is the normal force in this situation? Yes? Why is the normal force 98 newtons? Because gravity's pushing down on the ground with 98 newtons. And I got to be fussy. Newtons, not kilograms. Don't ever tell me that. Here in B, so we still have, what are the forces acting on this? Get the obvious one. I have mg, which was 98 newtons. I did the math in my head. But there's an extra force. Maybe someone off the page is pushing down on it, or a little invisible angel or something. Rowan, what's the extra force? How big? Which direction? Is this sinking into the ground like quicksand? Is it flying like Superman? Then the normal force is going to be a little bigger than mg. In fact, I can tell you exactly how big the normal force is because everything down has to equal everything up. How do I know everything down has to equal everything up? Are we sinking in the ground like quicksand? Are we flying like Superman? Then forces must be, I'm looking for what means letter B, balanced. So what's everything down? It's actually mg plus, oh, not 10, Mr. Dewick, 30. The normal force is larger. What was the normal force in part A? Exactly 98 newtons. How big is it in part B? Whatever 98 plus 30 is, I can do that in my head. 128, yes? So you'll notice on your formula sheet, there's no equation for the normal force. Instead, Savannah, do a good free body diagram and figure out how big it has to be. That's all I got. And you're not going to learn anything new in Physics 12. That's all I got. This is a job for a free body diagram. C. What are the forces acting on this? Get the obvious one. So I still have mg down at 98 newtons. Sam, what's the other force in part C? Do you see it? How big? Now here's what that means. Again, someone off the page that I didn't bother drawing in, or a little invisible leprechaun or angel or something. Something is applying an upwards force. And what that means is the normal force doesn't have to cancel out all of gravity. Do you know how much of gravity the normal force has to cancel out? You can do the math in your head. Antonio, I think you were right. Loud and proud. 48 newtons. Now let's write this out in case it was a tougher question. First of all, I would argue that the normal force is shorter than gravity now because 50 newtons is being taken up by something else. Sam, are we sinking into the ground like quicksand? Are we flying into it like Superman? Then everything down has to equal everything. That's about the only equation I guess I can sort of give you. So everything down has to equal everything up. Antonio, how would you get the normal force by itself? How would you move that plus 50 over? And you are correct then, you do get the normal force is 48, although you just did it in your head, great. But if you're wondering what if it was yuckier numbers, this is how I would go about it. Everything down has to equal everything. If it doesn't, then we must be either sinking into the ground like quicksand or flying into it like Superman. We'd have to be. Put your pencils down. This is hugely important. A scale does not measure mass. A scale does not measure mg. Rowan, what does a scale measure? I guarantee in your future, I'm going to be asking you to tell me what a scale reads. I'm going to say, tell me what the scale would read. I'm not asking you to tell me what the scale would read. Which force am I really asking you to find? In fact, all of you will pay money for this. A good amusement park ride, Logan, all it does is it messes around with the normal force. Right now, all of you are feeling a normal force of 1G. You're feeling the chair pushing up through you against your body with whatever your mg is. Everybody lift your feet off the ground right now. So right now, all of the normal force is coming through the chair. Put your feet back down. Okay, some of it now is being split. Some of it's coming through your feet. Most of it's still coming through your chair. You're used to that. All an amusement park ride does is it mucks around with the normal force, because we can't change mg. We're not God. But we can change the normal force. And you'll pay money for that. Put your pencils down. So the normal force is what a bathroom scale measures. It's the ground pushing up against you. I like example one. I like example one. I'm telling you right now, there's going to be a bunch of what I call elevator questions. You can try and memorize a different equation for each one of these, or Riley, if you're willing to humor me with a good free body diagram, we can derive this all. Read along with me. It says this. A man stands on a Newton scale in an elevator. What do I mean by a Newton scale? The bathroom scale that Rowan was standing on measures in kilograms. Let's pretend we have a physics scale that instead of calibrated for kilograms is calibrated in newtons. What does the scale read if the elevator is accelerating upwards at 3.2 meters per second? What's this question asking me to find? What's this question really asking me to find? If it says, what does the scale read, which force are we talking about? We're not talking about weight. Not talking about mass. It's not a force. Newton's is just for which specific force? The normal force. What does a scale measure? Normal force. When I ask for a scale in our free body diagram, we're going to find the normal force. Speaking of, this is a job for a free body diagram. Let's represent the man with a dot right there. What are the forces acting on this man? Get the obvious one. Good. mg down. Which way is this person accelerating according to the question? Can you say that out loud? Up. So which way must there be a bigger arrow? What's pushing him up? Well, the ground through his feet. But what force have we called that now? Good. Right here, you have a little bit of space. If you want to, you can write big W minus big L equals MA. Winner minus loser equals MA, because this is what we're going to use. Look at your free body diagram, Jackson. Who's winning? Up's not a force. Look at your free body diagram, Jackson. On your free body diagram, which force is, who's winning? Who's losing? What does winner minus loser always equal? What's this question ask me to find? What a scale reads. What's this question really asking me to find? No. You're missing out on the key point right now, folks. When I ask you for a scale, what am I talking about? By the way, if you haven't put a big star next to this, you want to put a big star next to this. This is hugely important. This is hugely important because I'm not going to be repeating myself over and over. What force am I really asking you to find, Riley? How would I get the normal force by itself in this equation? How will I move that mg over? There you go. Don't memorize this equation. We can derive it. It's going to be mg plus ma, or ma plus mg. I don't care which way you write it. I just have the habit of writing gravity first for some reason. Jackson, what's the mass of this person? Yep. G, 9.8 plus 72. What's A? The question told me. Yep. How do you know? Yeah, meters per second squared. What's the normal force? Get your calculators out and crunch this, please. I might be able to do it in my head. It's going to be 72 times 14. It's going to be 700. Nah. $72 times 9.8 plus 72 times 3.2 to get 936. This person's normal is mg. If I go mg, this is what they normally feel, 705.6. What are they experiencing through their feet right now? How big? They feel heavier. And this is why when a ride accelerates you up, you feel heavier. Has your mass changed? No. Has gravity changed? No. Which force has changed? The normal force. It's a very important force. Let's do another one. B. What if we're accelerating upwards at 2.5 meters per second squared? This is a job for a free body diagram. What are the forces acting on this person, Antonio? Get the obvious one. Which way? Down. Which way are we accelerating? So I know there's a bigger force pointing up. Which force is that? It's the ground pushing up through the feet. What are we calling that now? Good. What's my equation, Antonio? Who's winning? And if you want to, you can also say Fn. I don't care which. Who's losing? What's it going to equal? What does winner minus loser always equal? MA. Okay. What are they asking me to find? What the scale reads. What are they really asking me to find when they ask me to find what a scale reads? How do I get the Fn by itself? So you do have an Fn clue. Good. Yeah. Add the mg over. Fn is going to be mg. Don't try and memorize this equation because it'll change if we're accelerating down. It'll change if I add a few more things. We can derive it every time. Rowan, a good free body diagram, Newton's laws to figure out who's winning, and then winner minus loser equals ma. It's going to be 72 times 9.8 plus 72 times 2.5, which is what? 885? Okay. 886 if I went to 3 sig figs. And again, I think his normal was something like 700 and something. You would feel heavier. Are you actually heavier? No. Would you feel heavier? Yeah. Why? Ground's pushing up harder than you're used to. What if we're accelerating downwards, and then there's a part, let's call that part I, and then part II. What would the scale read in kilograms? Okay, so leave a little space on the end here. This is where we're going to change our answer to kilograms. This is a job for a free body diagram. What are the forces acting on this person? Kenley, get the obvious one. Good. Which way? Yep. There is a force up as well. Bigger, smaller, or the same size as mg. Which way are we accelerating in this question? So which way is winning in this question? So am I going to draw bigger, smaller, or the same size? Yes. It's still ground. By the way, can you see when this is in partial free fall, this person feels lighter because you can see the normal force is smaller than mg, and the normal is mg. What's my equation? Who's winning? Who's losing? What's that going to equal? What am I trying to find? What's right in front of the Fn that I don't like? Ooh. Oh, swappy dance. Let's plus this to that side, and at the same time, let's minus the MA to this side. We can do that in one step, I think. I find it really helps to draw those little loopy arrows because that makes sure I don't mess up my signs. And what happens is the MG just drops down like a domino, but there's a minus MA, and that's going to equal the normal force. Let's plug in numbers. The normal force is going to be M, 72, G, 9.8, minus M, 72, A, 5.2. No. I took care of that with my winner minus loser. I never need to put a negative in for the accelerations. With my winner minus loser, I took care of all the signs. That's the nice thing about this method. And I get 72, whoop, I don't. 72 times 9.8 minus 72 times 5.2. It's a typo, Mr. Dewick. Do you get 331.2? Yeah. Units. It's a force. Now, part II says, okay, what would that read in kilograms? Because most bathroom scales don't read newtons. Most bathroom scales read kilograms. How do you change a force into kilograms? Kilograms equals force divided by 9.8. Pause, look up, look up, look up, look up, look up, look up. I'm going to erase this. I'll bring it back in a second. M equals F over A. What's the acceleration due to gravity? No, what's the acceleration due to gravity? You all know this. If you want to convert any force in newtons into kilograms, just to see what the kilogram mass equivalent would be, it's divided by 9.8. Really what that means is any scale you've ever stepped on, it's just calibrated for Earth's gravitational field to translate that force in kilograms. So the mass, what the scale would read in kilograms, is going to be 331.2 divided by 9.8. If this was a kilogram scale, it would read 33.8. What was this person's actual mass? What's the scale telling them their mass is? 33 point. They're feeling lighter. Are they lighter? No. They would feel lighter. Why? Because the ground pushing up on them, the normal force has gotten smaller. That's what you saw on that little kid's face when we came over the first hill in the roller coaster. D. Still wants me to find the scale reading? No, Ben, what does it really want me to find when it says scale reading? Which force? Okay, you know what this is a job for? Free body diagram. Here's the person. What are the forces acting on him, Ben? Get the obvious one. Which way? Down. Which way are we accelerating? So which way is winning? So I know there's a normal force, but it's going to be smaller. I know that. By the way, how do I know there is a normal force? If there was no normal force, if this person was in free fall because there was no ground, what would this acceleration say exactly as a number? Not 3.72. What would it say exactly? 9.8. So I know there's got to be something slowing them down a little bit. Right? Who's winning? Who's losing? What's that equal? MA. How would I get the normal force by itself? Swappy dance. mg minus ma. Do you mind, Ben? I'm going to put the equals, I'm going to put the normal force on that side. Partly because I'm running out of room. 72 times 9.8 minus 72 times 3.72. By the way, the other thing I could do here, I'm asking you to find the normal force by giving you the acceleration. I would have no problem giving you the normal force and asking you to find the acceleration. How would you get the A by itself? How would you get the A by itself? Divided by M. Okay? Fair game as far as I'm concerned. 72 times 9.8 minus 72 times 3.72. I get 437.76. 437 point. You know what? 438. I'll go to 3 sig figs. Newtons. What if we're moving downwards at a constant velocity of 3.72 meters per second? You know what this is a job for? Free body diagram. What were you going to say? Pardon me? A is equal to 0 because of... Okay. Here's my free body diagram. Jabber, what are the forces acting on it? Get the obvious one. What else? Normal force, bigger, smaller, or the same size as mg? Pardon me?
Balance.
Balance. Oh, same size?
Yeah.
Why? Constant velocity, which means A is. So my equation gets modified a little bit. You know what? Normal force is the same size as mg, and by the same size, I mean equals mg. I don't even really need to go winner minus loser. It's a tie! It's going to be 72 times 9.8. It's going to be 720, take away 14 is 706, take away 704 points. I don't know. What do you get? 72 times 9.8. 705.6. I was going to say 704.6. 705.6 newtons. Now here's what that means. You ready? What's his normal? 705.6. This is why Einstein said there's no experiment that can tell if you're at rest or if you're moving at a constant speed, because you get all the same values moving at a constant speed as if you're at rest. Rowan, what if you jumped out of an airplane so that you were accelerating downwards at 9.8 meters per second squared and you stood on a scale? What would the scale read? Riley? 0. Yeah. 0. There's no ground pushing up. So even inside the elevator, now let's prove it. This is a job for a free body diagram. What are the forces acting on this person? Get the obvious one. Now, oops, mg. Riley, you said 0. Let's suppose we weren't sure. Let's stick a tiny normal force there just in case. Which way are we accelerating, Riley? Who's winning? And so you would say, well, it's definitely going to be gravity minus normal force equals ma. Yes? You would then say swappy dance to get the normal force by itself. And you would get the normal force equals mg minus ma. Is that okay, Riley? Yeah. What's m? 72. What's g? 9.8. Minus, what's m? 72. Riley, what's this question say we're accelerating at? What's this question say we're accelerating at? Find the number that has meters per second squared next to it and read me that number. What? And you get 72 times 9.8. Take away 72 times 9.8. In your head, what does that work out to? We've just proved that standing on a scale while you're in free fall. By the way, that's another way that I can prove that a scale measures normal force, because you still have mass in free fall. Gravity is still acting on you. You're falling. That's why gravity is acting on you. No normal force. I got a couple of cool videos and questions, but I'll start next class with those. For now, you can, on the homework, do section A. You can do number 1 from section B. You can do number 2. So I've finished the lesson, but I do want to talk a little bit about the International Space Station and some stuff, but that'll be next class, and I got a really cool video to show you next class. Let me